Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. This is the 18th lecture of numerical analysis. I will be talking about the Euler's method. But before Euler's method, in the last lectures, I derived the composite form of the Simpson rule and the trapezoidal rule. So this is an assignment for you. Okay, find out the composite form of the 3-8 Simpson rule, which is in your book. Remember, the formula for 3-8 Simpson rule is given, and your target will be to find out their composite form. That is your assignment. And definitely you need to do the preparation of the topic also. So now we finish with the numerical integration and differentiation. And today we will be talking about the initial value problem, which is the topic from chapter number 5. So the first topic in your course is the Euler method. Euler method is using for the solution of a differential equation. So let us consider a well-posed initial value problem. You can see that this is a first order differential equation. And you know from your MT201 that if you have a differential equation and you are looking for its particular solution, in that case, if this first order differential equation, so one condition is required to find out the particular solution. So you can see that dy by dx is the function of x and y. So you can see that on the right hand side you can have the dependent variable also. In this case, y depends upon x. X is independent variable and y is dependent variable. The value of the independent variable lies between a and b. So this is the interval you are going to consider. And since this is first order differential equation, so you need one condition, and this is initial condition given to you. Since the condition is given at the initial point, that's the reason it is called the initial value problem. So now let's see that how Euler method is computing the solution. As usual, I did the partition of the interval from a to b. This is the partition. Remember, in this case, we will be in the position to find out solution of this differential equation at x is equal to x0, at x is equal to x1, and x is equal to xn. Again, we assume that the data is equally spaced data. The data is equally spaced data means that xj plus 1 minus xj is equal to h. And if you want to link xj with the initial point a, so this is the way we are linking them. And this is common for you people. The value of j starting from 0 and reaches up to n, because we are covering the complete domain in this case. In this technique, y of x, the value of y which satisfies this differential equation is called the solution. So we assume that y is unique solution of the initial value problem. So this is the complete problem. And we assume that y of x is the solution of this initial value problem. So let's use the Taylor series. Do the expansion by Taylor series. So y at xi plus h is, you know that this is y at xi plus h multiplied by y prime at xi plus h square divided by 2 multiplied by second order derivative 8. Since I stop at this point, so that's why I use the gamma I instead of xi, and this gamma A having the same rule which you know from the beginning of numerical analysis, that how we are selecting this gamma I. Second order derivative of the function. But now if you look at your problem, dy by dx is y prime is equal to f of xy. So let us substitute the value. Y prime is equal to f of xy. So let us substitute this value in this expression. So what we will get? You know that the data is equally spaced. So xi plus h is equal to xi plus 1. Y of xi, h multiplied by we substituted the value of y prime from here. Now let's ignore this error term. Let's ignore this error term. So what we are getting? I assume that let's assume y at xi is equal to wi. This is just the notation. Wherever there is wi, I mean that this is the solution of the equation at x is equal to xi. If this is the case, then the Euler method is, you can see y at a is x naught. So the value of I is equal to 0. I am getting y at x naught, and y at x naught is equal to y at a, and y at a is equal to alpha. So that's the reason I'm writing from this condition that y naught is equal to alpha. And if you look at this one, this is a y at xi plus 1. So according to this notation, this will be wi plus 1. This is equal to wi plus h xi, and y of xi is wi, and the value of I is starting from 0 and reaches up to n. This is called the Euler method. Remember, in Euler method we are not getting a very good accuracy, but anyhow this is the starting that we can find out solution of the differential equation with the help of this technique. So let us consider an example. Before that one, you can see over here, if I have 2 points xi and xi plus 1. So wi is the solution at xi. I will say this is the solution. In order to get the solution at xi plus 1, we need the solution at the previous point. And previous point is xi. So this is the solution at the previous point. I mean the solution at xi. The distance between these 2 points is given by h, which is the step size. You can see over here, and if you look at this function, this is the function at this point. Its x component is xi, so corresponding to xi, your solution is wi. And you can see in this function is this y is the solution at x. So I can see wi is the solution at xi. So Euler method is using two consecutive points. If solution at the previous point is known and the function is known, then we can find out the solution at the succeeding point. Now let's consider let's go for the MATLAB code to approximate the solution of the initial value problem using the Eulers method. This is the normal command CLC, which clear all the parameters, variables you have defined before. And similarly, I say clear R, so it also clear if you have in the background, if you're having some variables defined, so this command will clear them. Just I have taken n is equal to 2, and depends upon how many points do you have. So in this case, I consider just 3 points. That's the reason. I say A is equal to 0, B is equal to 1. It depends upon your problem. So this is a initial point of your domain, and this is final point of the domain. You can see these are the mesh points. These are the mesh points. The value of A is known, the value of B is known. Find out the distance between the two consecutive points. What we are doing, B minus A divided by N. That gives us, I have used small n here and capital N here. This is just the notation which I use in the program. So this will give you the step size between two consecutive points. Let us generate xi's. As usual, xi is equal to a plus I minus 1 into h. What this loop is doing for you, I is equal to 1, so it's a plus 0. So it gives you initial point of your domain. When I is equal to 1, so this will give you a plus I is equal to 2, 2 minus 1 is equal to, so a plus what h is equal to x1. Similarly, when I is equal to 3, so x3 is equal to a plus 2h, and that will give you next term. Remember, I'm not starting from 0. The reason is straightforward. As I told you before also, that in MATLAB, if you are assigning 0 to this I, that will give you an error. So in my program, x1 is for x0, x2 I use for x1, x3 I use for x2, and so on. So xn plus 1 will be using for x small n. This is the way you already know. So what you are doing in this loop, you are generating the points of your mesh. This is the Euler method. Just write the Euler method. So let's use. What I am saying, W1 instead of naught, I'm using 1. W1 is equal to alpha. So that is the first line. Second line, let's generate. The value of I is starting from 0 up to n. So instead of 0, I'm using 1. So it will be starting from 1 and will be reaching up to n plus 1. But remember, this should be n minus 1. Why? Because at x is equal to 0, I'm getting W1, which is your initial point. I is equal to 2, that will be the solution at x is equal to, I is equal to 1, so this will give you W2. W2 is the solution at x2. Since I'm starting from 1, so I will say, because when I substitute n is equal to I is equal to n, I am getting Wn plus 1. Remember, when starting from 0, Wn plus 1 is not there, so I will say this is minus 1. There is minus 1. So it's starting from 0 reaches up to n minus 1. Why? When I substitute I is equal to n minus 1, I will get Wn, and Wn is the solution at this point. Why am I writing n here? Because I have started from 1 instead of 0. Exactly, Wi plus 1 is equal to Wi plus h multiplied by function f at xi and corresponding solution at wi. And then n. This is a small e, not capital E. This window has changed. So when I is equal to 1, you are getting W2. W2 is equal to W1, which we have defined before, plus H you have defined before. F of, this is the function. And you know that if you are defining a function file for it, if you are writing your function over here. So replace x by x1 and y by w1. So x1 is coming from here and w1 is coming from there. So you will get w2. When I is equal to 2, so this will be w3, you need w2. w2 you have computed in the when I was equal to 1. Now h is common, f of x2 is coming from here, and w2 you computed at the previous stage. And this process will continue until when n is equal to, I is equal to n, wn plus 1. I told you I started from x1, so this will be xn plus 1. So when I substitute I is equal to 1, I am getting wn and wn plus 1, and wn plus 1 is the solution of your differential equation at x is equal to b. In this case, my b is equal to x capital N plus 1. So you can see that this is just a small loop, and this loop generates the solution for you at these mesh points. For example, if you are having this differential equation, so you can see that dy by dx is equal to f of xy. So this is f of xy in your case. Of course, you have to use it over here. The domain is starting from 0, reaches up to 1. That's the reason I have taken it from here. And y at 0, that is the initial point, is the solution is 0.5, which was your alpha. And h is equal to 0.5. So when I use step size h is equal to 0.5, my x0 is 0, x1 is 0.5, and x2 is 1. That's the reason I have used n is equal to 2. But here you are generating 3 points because I am using x1 for small x0, capital X of 2 for small x1, and capital X of 3 for small x3. So you can see that if you solve this problem with the help of this program, so you can see you will be getting these values. So y at 0, this is given to you at 0.5, and y at 0.5, which was your x1, y at 1 is given by this one. So if you use this computer code, this will give you the solution at x is equal to 0, x is equal to 0.5, and x is equal to 1. I didn't wrote that in detail. I leave it for you that do the calculation yourself and get the solution with the help of this MATLAB code. Straightforward, you can see just you are familiar with these things from the very beginning, and this is the only loop which we introduced. Remember, you can't use capital E, and this loop, this should be small e. So whenever you are writing your computer code, use small e, not capital. That will not give you, that will give you an error. Let's consider an example. The example is use Euler method to approximate the solution of the initial value problem. So I'm taking an example. Dy by dx is equal to this term. The value of x lies between 1 and 3. Y at 1 is given to you, that is 0, and use the step size h is equal to 0.5. When you start from 1, so 1, 1.5, 2, 2.5, and 3, these will be your data points. So let's identify the things. And your formula, this is your function. This is your x naught is equal to x naught plus h. H is 0.5, so 1 plus 0.5 is 1.5. x1 plus h is 1.5 plus 0.5 is 2. x2 plus h is equal to 2 plus 0.5 is 3. And x3 plus h is 2.5 plus 0.5 is x3. So these are the data points when you are using your step size. H is equal to 0.5. So these are the points, these are the mesh points, and the target is to find out solution at these points. Means that you need a W naught is there, which is given to you. You have to find out W1, which will be the solution at x is equal to 1.5. W2 will be the solution at x is equal to 2. W3 will be the solution at x is equal to 2.5. And W4 will be the solution at x is equal to 3. That's the reason I'm using. W naught is a solution at y is equal to x naught. And y at 1 is given to you, that is 0. Just to substitute the values in this formula, which is the Euler formula. So when I is equal to 0, I'm getting W1. You can see over here, this will give you W naught plus H, f of x naught, W naught. So replace x by x naught and y by W naught and your function. So this will be 1 plus W naught by x naught, and this will be W naught by x naught whole square. Now straightforward, W naught is known to you, that is 0. The value of h is known to you, which is 0.5. This is 1 you are getting here. W naught is 0, so 0 divided by 1 is 0. And 0 divided by 1 is 0. So W1 is equal to 0.5. It means that 0.5 is the solution of this differential equation at x is equal to 1.5. So if you have the exact solution, replace x by 1.5, that will give you the exact solution, and do the comparison with this solution. That will be your corresponding absolute error. Let's find out solution at x2 is equal to 2. So let's substitute I is equal to 1 here. That will give you W2, which is there. That will give you W1. W1 you have computed. H. Now this time replace x by x1 and y by W1 in your function. So that's the reason you can see 1. W1 divided by x1 plus W1 divided by x1 whole square. Now W1 is known to you. W1 you have computed previously, 0.5. The value of h is 0.5, which is coming from there. 1 plus W1 is 0.5 divided by x1. The value of x1 is 1.5 plus W1 is 0.5 divided by x1 is 1.5 whole square, and if you do this calculation, you are getting 1.2222. So this is the solution of your differential equation at x is equal to 2. So if you have the exact solution of this problem, then replace x by 2, you will be getting the exact solution, and this is your approximate solution. The difference between the two will be the corresponding absolute error. We compute solution at this level. Now let's compute it 2.5. Euler method. Now let's replace I by 2. When replace I by 2, so you are getting W3 is equal to W2 plus H. Replace X by X2 because the value of I is 2, and Y by W2 because this time the value of I is 2. So you can see it over here. You computed the value of W2, which was 1.22. The value of H is 0.5. W2 is 1.222 divided by X2. X2 was 2. And similarly, W2 divided by X2. And when you do this calculation, this will give you the solution of your differential equation when X is equal to 3. When X is equal to 3, so this is the solution of your differential equation at X is equal to 2.5. Remember, you can see here that when you are computing the solution at X is equal to Xi plus 1, so you are using the information at the previous point. Solution at the previous point and function at the previous point. You got it? Now let's go for the last one. When I is equal to 3, so this will give you W4 is equal to W3, H multiplied by, now the value of I is 3, so X3 and W3. W3 you have computed here. So replace X by X3 and Y by W3 in your function. Now W3 is there 2.2145, X3 is 2.5. Just substitute the values over here, and now when you simplify it, you got the solution at X is equal to X4, and this is final point of your domain. So we computed solution at all the points from the domain. This equation having exact solution is X tangent log of X. Remember, in numerical analysis, my target is not the to obtain this solution analytically. I'm focusing on the numerical solutions. So let's look at the table. W0, W1 which you computed, W2 you computed, W3 and W4 so coming from your calculation. And when I replace X by 1 in this equation, you are getting Y at 1, and of course this is 0. This is the exact solution. Replace X by 1.5 in this equation, you are getting the exact solution. X is equal to 2 over here, you are getting this is the exact solution. When X is equal to 2.5, this is the exact solution, and when X is equal to 3, so this is the exact solution of your problem coming from here. The difference between Wi and Yi, that gives you an error. So this is corresponding absolute error. So the absolute error at 1, that is 0. Absolute error at X is equal to 1.5 is given by this term. Means that this is a 0.14. When X is equal to 2, the error is 0.43, and when X is equal to 2.5, you got the solution. In this case, the error is 1.04. And when X is equal to 3, so the error is 2.3. You can see that when we are moving away from the initial point, the error is increasing. And if you look at this problem, the step size is large, 0.5. So the errors are not that small, they are large. So it tells us that it depends upon the step size H also, which will be clear from the next example, that when I reduce the step size, so the accuracy is increasing. But I told you that with the help of this technique, errors are not that good. But anyhow, this is the initial method to find out the solution. The same problem I am considering with slight modification, and the modification is use the step size H is equal to 0.2. This is your Euler method, but this time the step size H is 0.2. The domain was from 1 to 3 you saw in the previous example. So there were 4 mesh points. Now in this case they will increase. I just use the general equation. W naught is the condition coming from there. When you are using h is equal to 0.2, means that your points are 1, 1.2, 1.4, 1.6, 1.8, 2, 2.2, 2.4, 2.6, 2.8 and 3. So you can count now how many points do you have. So what I did here, I just substituted the value of the function, and you know that value of the function was 1 plus y divided by x plus y divided by x square. So I just substituted that value. I replace x by xi, you can see here. I replace y by wi, which you can see over there. The value of I is equal to 0 up to 10. Because I counted the mesh points. X naught, x1 which is 1.2, x2 and so on, you can reach up to. So they give you the mesh points as I discussed before. Now let's replace I by 0. So you are getting W1. W1. There will be W naught, W naught, W naught divided by X naught. So in this case, your X naught is 1 now. I just produced it in the table form. You have to do the calculation yourself. When I is equal to 0, this will be W1 is equal to W naught plus H, which is 0.2. 1 plus W naught divided by X naught. X naught is 1. W naught is 0 divided by X naught. So you can see that this gives you 0. This is 0. H is 0.2. 0.2 multiplied by 1 is 0.2. So you can see that this is the solution. This table, this column corresponds to the solution. And I wrote the numbers up to 5 decimal places. When I is equal to 1, so this will be W2. W2 is a W1. W1 you computed here. W1 divided by X1. So X1 is 1.2. And when you substitute the values over here, this is your particular, this is your approximate solution. And similarly, I is equal to 2, you are getting W3. W3 is W2. W2 you computed here. W2 is there, X2 is there, which will be 1.4. And when you simplify this one, you are getting the corresponding solution at X is equal to 1.6. And this process will continue until you reach up to 10. When you reach up to 10, this will be W11, W10, W10 divided by X10, W10 divided by X10. You can see here, I started from X0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So W11 is the solution of your problem at when I is equal to 10, at X is equal to 3. So this is the column corresponding to the approximate solution of your problem. And I told you the exact solution. The exact solution, as I told you before, the exact solution is x tangent log of x. So when you replace x by 1 and y is equal to x tangent log of x, you are getting this solution. At x is equal to 1.2, this is the exact solution. And finally, when x is equal to 3.1 and y is equal to x tangent log of 3, so this is the exact solution. Now the difference between these two columns, the difference between these two is 0. The difference between these two is 0.02. The difference between these two is 0.05. The difference between these two is 0.09, and so on. Now you can see as compared to h is equal to 0.5, you can see that your error is smaller. So when you are decreasing it further, we are expecting that this error will be decreasing. You saw in the previous example as well as in this example, when we are increasing the value of x, the error is increasing. So this is the case when you're having 11 points in your mesh, then these will be your approximated solutions. Let's go to another technique, which is modified Euler method. Consider the initial value problem. This is as previously we saw, this is the differential equation. This is the domain, and since first order differential equation, so at the initial point your solution is alpha. Mesh points: A is equal to x0 less than x1 less than xn is equal to b. Step size, I told you the data is equally spaced in the previous case, so again it is equally spaced data. So these two relations they coincide with each other. Wi, this is the Wi is the solution of the differential equation at x is equal to xi is usual. Then the modified Euler method is given by this formula. Now look at this one. Again, this Wi is the solution at x is equal to xi of your differential equation. And Wi plus 1 is the solution at x is equal to xi plus 1. So you can see that these are two consecutive points. You are looking for the solution at this point. So in Euler formula, solution at this point plus the distance between the 2 points multiplied by value of the function at x is equal to xi. Straightforward. Now, slight modification in the technique. Remember, solution at the previous point, it is using here also. But focusing on the value of the function, you can see that this is a value of the function at x is equal to xi. And if you look at this point, this is value of the function at x is equal to xi plus 1. And the function you are seeing that this is independent variable and this is corresponding dependent variable. So when I replace x by xi, I'm getting yi, which is clear from here. In a similar fashion, I should get, when I replace x by xi, I should get yi plus 1. Wi plus 1 I have to use here. But remember, Wi plus 1 you are going to find out. So when I use Wi plus 1, this will become an implicit equation. And it is not necessary that you can extract Wi plus 1 from here and can combine with that one. Maybe, but maybe not. It depends upon your function. For example, your function is f of xy is equal to x plus y. So I can write, shift y to the other side. So at x is equal to xi plus 1, that will be wi plus 1. I can shift there to this one and can play with it because it having some coefficient. But remember, it is not always possible. That's why in modified Euler method, they are using Wi plus 1. This is coming from the Euler method, if you remember the previous slides. Wi plus 1 is equal to Wi plus h into f of xi wi. So value of the function at x is equal to xi plus 1 is a wi plus 1, but has been used the Euler method here. Now if you look at this expression, xi plus 1 is known, it's coming from our mesh points. Wi is value solution at xi, which is known, it's using here also. Xi coming from your points, wi it's coming from the previous point. So what modified Euler method did, compute function at xi and function at xi plus 1 and then taking their average. So add them and divide by 2. So you can see it's exactly like Euler method, solution at the previous point plus the distance between the 2 points. But this time value of the function at xi and value of the function at xi plus 1. Add them and divide them by 2. So it means that you are taking the average value. This method is called the modified Euler method. And this is also coming in RK method of order 2 also. This is a special case. Let us consider an example. Use the modified Euler method to approximate the solution of the initial value problem. This is the differential equation. This is your domain. At the initial point, this is a solution given to you, and use the step size h is equal to 0.5. Let's identify the values. This is our function, y by x minus y by x whole square. X naught is 1, x naught plus h is 1.5, and x1 plus h is 2. So you are having just 3 points. Solution at this point is known. Find out the solution at x1 and solution at x2 using the modified Euler method. This is the modified Euler method. Solution at x is equal to x naught alpha. Alpha value is with you, and that is given by 1. So we can see it over here. Now let's substitute for x is equal to x1. Replace I by 0. I divided this into different pieces. I denoted this f of xi wi by a naught, which you can see over here. When I is equal to 0, I have f of x naught w naught. So I denoted that by a naught. This is just the notation I'm using. You can use any other notation r. You can straightforward substitute the values in this equation. I'm dividing this into pieces so that the possibility of error decreases. So in your function, substitute x by x naught and y by w naught. So w naught by x naught, w naught by x naught whole square. W naught is known. So this is 1 divided by x naught is known, 1 by 1 minus 1 by 1. So 1 minus 1 is equal to 0. Remember, this is the value of the function at x is equal to x naught. Now let's find out this value. I represented this by I used another notation. I represented that by b naught. B naught is, remember, I'm substituting I is equal to 0. So this is a w naught plus h into f of x naught w naught. W naught plus h f of x naught w naught. F of x naught w naught, I noted that by e naught. So you can see I use e naught here. Now w naught is 1, h is 0.5, and a naught I have computed is 0. So this portion will become 0, and b naught is equal to 1. Let's find out the value of the function. So remember, I is equal to 0. F of x1, w naught plus h f of x naught w naught. I represented that by b naught. So that's the reason I'm using for this one, x1, and this was my b naught. You can see it over here. So replace x by x1 and y by b naught in the function. So this is the function, b naught divided by x1, b naught divided by x1. B naught you have computed, that is 1. divided by x1, you have 1.5. B naught is 1 divided by 1.5, and if you do this calculation, this is the value of the function, this one. Now this is known, which I represented by A naught. This is known, which I represented by B naught. So what will be W1? W1 is equal to W naught plus H divided by 2. This I denoted by A naught, and this whole I denoted by C naught. So A naught you have computed, C naught you have computed, substitute the values, and this gives you solution of your differential equation at x is equal to 1.5. Remember, when the exact solution is known, so replace x by 1.5 in the exact solution, that will be exact, and this is approximate. The difference between the two will be the corresponding absolute error. I computed solution at this one. Now compute solution at x is equal to 2. So replace I by 1 here. You will be getting W2. So I'm representing f of x1 W1 by A1. W1 plus h f of x1 W1, I represented that by B1. And I represented this whole function for I is equal to 1 by C1, and then I will compute the value of W1. So let's see. This I told you before. W1 is known, x1 is known. Substitute the value, and this is the value of your A1. The value of, so this is this portion, and your formula B1 W1 plus hf of x1 W1. This one, which is this portion, and your formula f of x1 W1 is A1, which we used before. Now W1 we computed, A1 is coming from here, h is 0.5, and when you substitute the value, this is the corresponding value of this term. Now let's find out f of. So I is equal to 1. So this is x2, and this is our B1. So replace x by x2 and y by B1 in your function. The value of B1 is known, you have computed here. X2 is known, which is 2. B1 is there, and when you substitute, you are getting C1, and C1 is the value of the function at x is equal to x2. Now let us find out the value of W2. W2 is W1 plus h divided by 2. This was my A1, and this was C1. So A1 plus C1, you can see it over here. A1 is known, is coming from here, C1 is coming from there, and when you substitute, this is the solution of the differential equation at x is equal to 2. This is the exact solution of your problem. You computed, this was the initial condition given to you, this was your this was your W you computed, and this is your W2 which you computed here. When you replace x by 1 over here, so that will give you 1. The corresponding difference is 0. But remember, this was the condition given to you, and normally the condition is coming from the exact solution. When you replace x by 1.5 in this expression, you are getting this value. This is your approximated value. The difference between the two is the corresponding absolute error. And when you replace x by 2 in this equation, you are getting this is the exact solution. This is the approximate solution which you got here. The difference between the two is 0.013. Now, if you do comparison with the Euler method, so in this method our error is small as compared to the Euler method. So solution with the help of the modified Euler method, they are slightly better than that of the Euler method. Now let's consider another example. Use modified Euler method to approximate solution of the initial value problem. The same problem I am taking, but this time I reduce the step size. There I use the step size at 0.5, but now I'm using step size is 0.1. The value of W naught is in the previous example. This is the previous example, but I changed the step size. Exact solution, which I showed you right now. Go for the solution. This is your function, but remember step size is 0.1. X naught is equal to 1. 1 plus 0.1 is 1.2, then 1.1, 1.2, 1.3 up to 2. So these are your mesh points in this case. And you can see that how many they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you're having 11 points. I did a case in Euler method. So again, I'm taking 11 points here. This is your modified Euler method, which we discussed. W naught is coming from here. This is 1. I'm using the same notation. I just denoted this portion by AI, this portion by BI, and this function by CI, and then got the value of WI plus 1. So accordingly, AI is equal to f of xi wi, BI is this portion, wi plus h into f of xi wi. But f of xi wi, I denoted that by ai, so this is wi plus h into ai, which is the simplified expression. See, value of the function I told you, this I denoted, this will be xi plus 1, and this portion we denoted by bi, so you can see it over here. Replace the function in the function x by xi plus 1 and y by bi. So this will be bi divided by xi plus 1 and bi divided by xi plus 1. This is my short notation. And finally, wi plus 1 is equal to wi plus h divided by 2. This function value I denoted by ai, and this I denoted by ci. It's totally up to you if you are saying that I am just using a single expression, substituting the values totally in this expression, you can do that, but the possibilities of error increases. So that's why I splitted this into small pieces so that I can do my calculation. The value of I is starting from 0 and it reaches up to 10. If you count these points, these are 11 points. Starting from 0, so these are 11 points. I'm not computing all the values separately, but I produce the table for you. Rest you have to do. This is the formula, this is the same equations notations which I used, you reproduced. And this is the table for of absolute error, approximate solution, and exact solution. So you can see here, when I is equal to 0, A naught, B naught, C naught, and substitute the values in this expression, you are getting the approximated solution. When I is equal to 1, compute A1, B1, C1, and accordingly W2, and W2 will be your solution, which is given by this. Then I is equal to 3, so A3, B3, C3, W4, and W4 will be this solution, and this process will continue. Finally, when you replace I by 10, so A10, B10, C10, and that will give you W11, and W11 is this value. So this column corresponds to the approximate solution which you are getting from these equations, and this is the exact solution. This is the exact solution I told you before. This is the exact solution which I showed you in the previous slide, at x is equal to 1, 1.1 and 2. So these are the exact solutions, these are the approximated solutions. The difference between two is the corresponding absolute error. Now you can see when h was 0.5, h was 0.5, what was your absolute error? And when I reduce h is equal to 0.1, then you can see that your error has been reduced. Yes, you can see the trend when the value of x is increasing, error is decreasing slightly, but this is almost 10 raised to the power minus 4. 1.4 into 10 raised to the power minus 4, 2.3 into 10 raised to the power minus 4, and this is 3.9 into 10 raised to the power minus 4. So you can see now that in case of the modified Euler method, the errors are small as compared to the Euler method. Also, you saw that when we are decreasing the step size, accuracy is increasing. So this is a lecture about the solution first order differential equation initial value problem with the help of the Euler method and Euler modified method. I hope that the points will be clear, but I will be suggesting open your register, pick the pen, do the calculation, so that it become clear to you that how this has been derived.